so what I'll talk about is related, of course, to the course. It's machine learning engineering, but then specifically how that enters medicine and healthcare. But what I will be saying is, just a second. There you go. It's related to the module that you're currently in, right? About machine learning in practice. So as Satish has provided you with lots of good material and a good overview of what it means to do machine learning in practice, I know. And now we'll look at an example of this in a sense. Okay, so it's about machine learning in medicine. And as you may have heard about, because Satish is also working on machine learning in medicine, there's a lot going on in medicine related to machine learning. And sort of the short story why you're interested in machine learning in medicine is what I'll provide now. So you know very well that there's a lot of interesting things going on in machine learning related to various kinds of data, for example, image data. And so you know that now these days, more than ever, you can create systems that are able to do, for example, this task of recognizing objects in image or video, and then classifying those objects. So detection and classification and so on. That's one area where you can do a lot these days, much better than ever before. But as you also are aware, likely, these are very generic techniques. The techniques you use for doing this are very generic, so you can use them for other related tasks, for example, in medicine. And in medicine, medical imaging is one very important part of medicine, used a lot in diagnostics. You are very often collecting images of some sort using advanced machines for image collection, like MRI. And that's the thing on the right here. It's an MRI of a brain. And then you're interested in what can you see in this image, right? So you use information from that image to figure out what can potentially be going on, potential disease or some disease process or effect of therapy or prognosis or whatever. So imaging is very core to what's going on in a modern hospital, and increasingly so. But okay, so then if on the left side, you can now these days find objects and classify them very much better than ever before. Of course, you're then interested in applying that on the right side, like saying, find a brain tumor and perhaps classify it according to severity. And you can do exactly that. So you can apply the same methods on the left to the problem on the right. So Tesla on the left and tumor on the right. And it's essentially the same problem. And you are also aware that there's a lot more going on the left side, sort of in general applications of machine learning, than beyond only this task. But the message is the same. These are generic techniques. You can apply them then to related problems in medicine. So that's why you get a lot of results or interesting findings in medicine. Okay. But again, this goes beyond medical imaging, and you're seeing interesting preliminary proof of concept results across medicine or healthcare, from sort of patient contact, like when the patient is first visiting the doctor, and the things that go on there. Okay, there are increasing use of machine learning and artificial intelligence and robotics and these kind of things in that domain, all the way to drug development, like developing new drug treatments for various diseases. There's also a lot of machine learning going on in modern drug development, especially on the research side. So the vision for AI or machine learning, which is more precise than saying AI in medicine, is that you want to try to provide solutions across the entire span of medicine. So here, like organized more or less from a lifespan perspective, from like stem cell research or regenerative medicine. There's a lot of machine learning being applied there, or trying to make something useful in that end, all the way through like health registers, wearables, mental health assessment, pre-hospital services like ambulance service, then radiology, which is images, drug discovery as mentioned, figure out if there are different subgroups of a group of patients having some specific disease. See if you can figure out whether there are meaningful subgroups of these patients that will respond differently to different treatments. So making medicine more personalized. There's a lot going on there. Patient safety and risk, and even hospital management, like the flow of patients in a hospital or through the healthcare system. And if you talk to the modern hospital, like the directors of hospitals and so on, there's a lot of talk on having home hospitals or hospital at home. So that's something that clearly will come. Like there will be fewer, there will be a high threshold for actually being put in a bed in a hospital. You will more often than now be at home and then monitored by various sensors and so on. So hospital management, the home hospital, the smart hospital, all these kind of things. Okay, so that's the vision. You see the indications that these technologies in modern machine learning can be applied across this entire span, and therefore there's a lot of attention on this field you can call medical AI. And what is medical AI? Well, surely it consists at least of two core components: medicine, the domain, and machine learning engineering. Because as you know, not everybody knows this, but you know this, when people say AI, you're really talking about machine learning these days. And if you're talking about machine learning and applying machine learning to solve problems, you are really actually talking about more specifically machine learning engineering, and not say machine learning model development. It's you need the entire engineering perspective to do something practical, like Satish has likely told you many times, and it's a very important point. Okay, so that's medical AI. It consists of medicine, machine learning, engineering, and both are core for making this work. And then, so let's think about where medicine and machine learning development interacts in the development and use of machine learning in medicine. So Satish has shown you this machine learning project lifecycle. So I will not dwell on it again, but there's an interesting point here. I think in the interaction between medicine and machine learning, and which it goes beyond just medical AI, but in any AI applied to some domain, there's an important point to be raised there. But okay, so quickly going through, but I know this is repetition from what Satish has said. He has told me that he has talked about this. But the first thing you need to do, as you know, to go through to successfully perform a more practical machine learning project is to have to scope out the project. You have to figure out what problems can or should be solved. You have to somehow gauge the feasibility, technical feasibility, and the more domain-specific feasibility, like in medical imaging. Is it feasible to solve the problem using the data that the inputs that you can have? Like, is it medically feasible, even theoretically possible? And you need to define your goals and your metrics, and then you go through this loop that you know of, where you in the first sort of part you study the data, as you've done many times now, and there are always questions about quality of data, and you know, also in machine learning, the labels of the data being of sufficient quality, then you have to get the data that lives in some database likely or something like that, and then exploring it, preparing it. Then you get to the machine learning part where you sort of explore and maybe develop new machine learning models, figure out some good candidate models that you can apply to your problem or create some new ones. Then you optimize them, right? And maybe construct ensembles, stuff you know about. This is really into the machine learning part. And then very importantly, you need to evaluate and validate what you have in the modeling part. You have to look carefully at the mistakes the model makes. So that could be like in a cancer diagnosis, you have some pictures of skin lesions, input, output is cancer, not cancer. You really need to analyze the mistakes in terms of what you're actually trying to solve. So say in cancer diagnosis, that the worst mistakes will be false negatives, right? That you say it's not cancer when it is actually cancer. That's maybe the worst mistake. But also the true positives are troublesome, of course, for slightly different reasons. Stress of the patient, the cost to the healthcare system of digging further into the problem if you have a false positive, and so on. But you need to analyze them, like count them up, like your confusion matrices and so on. And you need to try to figure out why the mistake happened and see if you can go back and make it less likely to make that kind of mistake. And then you also need to figure out what features are your model leaning on, because that tells you, gives you an indication of things you can improve. So here's sort of the basic, what you learned about in the first module of the course. It was a lot about this modeling part with some exploring preparation of data, but not that much focus on it. So this is sort of, module 1. But now in module 3 of the course, or part 3, you know, that you also, if this is supposed to do anything useful in the world, you need to deploy it. You need to put it into production somehow. And then you also know that when you do that, it will not perform as expected typically, or there will be issues, and you will definitely need to monitor the solution that you've created and update models and data and so on. And you also importantly need to monitor whether you're actually solving the problem that you scoped out in the beginning. So maybe you're monitoring certain more technical things like the accuracy, the false positive rate, maybe the throughput, latency, these kind of things. But one must, of course, not forget that you're trying to solve some goal, some big picture goal, which is not necessarily captured by these more technical metrics. So you monitor that as well. And then you go through this loop over and over, as you know. So it's a loop, but also there will be, of course, should be edges in between here as well. Like you're not only going through the entire loop, but you can jump back and forth, as you know. Okay, so that was known, but now back to the medical point of view. When you're trying to make some solution into a domain, you need domain expertise on board, right? So the domain experts should really be in the team somehow, as embedded into your team as possible, because they will come in at least here, or they should. That would make it everything better. They should definitely be part of figuring out the big picture, like what problems should or can be solved, and the feasibility from the domain, like the medical feasibility. And for sure, the data, the quality of the data and the labeling of the data, that's very tough to do without domain knowledge in such a complicated domain as medicine and many other domains. So if you can get a hold of a domain expertise there, that helps a lot. Also the exploration of the data, you would really like to have when like you have explored data through plots and statistics and all these kind of things and trying to understand what the data tells you before you start making machine learning models. The perfect setup there would really be to do that side by side with some domain expert to really see, to understand the data. And then for sure, when the model makes mistakes, as they always do, you need to analyze them. And then it's hard to analyze them if you can't really understand or come up with good reasons why these mistakes happen, and whether or not they are serious and so on. So you would actually want the domain person in the modeling part as well. And then of course also in the monitoring, both this part of the monitoring, but also the business impact, as we may call it. Okay, so this is the more ideal setup. You have the domain expertise in the whole process of developing a machine learning project. And this goes beyond medicine, of course. So this combination in medicine of having like the software engineer and the domain expert as part of this whole thing is the way to go. Okay. Because if you don't do this, you may end up, for example, solving problems that are not interesting really in the domain. They sound interesting to us, like technical, the software engineers, but maybe they're not that interesting. You're actually solving the wrong problem, or you're measuring whether you solved it in using the wrong metric, and your exploration of data actually uncovered that your data doesn't support what you're trying to do, but you didn't notice because we didn't know the domain well enough. The mistakes your model makes are maybe horrible, meaning that the model, even if it's performing superficially well, it doesn't work. It will never work. It cannot work. It's the mistakes are too horrible. That could happen. And you're monitoring only technical performance, but you're actually not monitoring whether you're actually helping anyone, if this is related to patient care, say. Okay, so there are lots of traps you can end up in without this, and there are more. So this is on the development of the system level, but there are other challenges as well, and there are many. Many of these are not just for medical, of course, but they're all very, very much they are true challenges in medicine, all of these. In other fields, you may not care that much about all of this, but they are general. And it's stuff like, you know, that you need training data to create machine learning models, and some machine learning models needs a lot of training data. And the quality of it's not just the amount, it's also the quality. And sometimes small data sets, but high quality, are much better than large data sets with less quality. And that leads you often to issues of data access, of course, and privacy. In medicine, that's obvious, but also in most other fields where the data is collected from people's behavior or just directly from people. You have, of course, issues of privacy, as there should be, and the law. And you need to label data. That's not easy. You want to do it using as little human resources as possible. So maybe you have some labels that you come up with that are sort of part of the data, but maybe they're not actually the actual labels you're after, but the best you can do. And yeah, so you need to think about how to define the data. And the black boxiness of many methods, even relatively simple methods like random forests have an aspect of black boxiness, even if they're built on decision trees that are not black box at all, completely open. There are many decision trees, there's lots of randomness, and you get some black box problem there. And then, of course, if you move to deep learning models that haven't been really part of the course, part of this course, but you are probably aware that these deep learning models, these artificial neural networks, are the ones behind a lot of the technological development last few years. And these are definitely, they have a definite character of being a black box. So then you need explainable AI. You need to be able to, ideally, you want to be able to answer, you want the system to be able to answer these questions. So you need to clarify these questions. And then, yeah, so on and so forth. So just to, yeah, so it's clear there are all these issues and more. You can easily put in more here. They all, if you go back to medicine, they require some kind of dialogue or common understanding and common work between the domain expertise, like the medical doctors kind of people and software engineers, and also particularly in medicine, but also other domains, regulatory agencies like the government and so on. Like how much black boxiness can we tolerate in a medical diagnostic setting? Well, that depends on sort of what the medical community can tolerate, but also the law. We're not allowed. You have to give an explanation, for example, mostly currently, and maybe that's not possible, but your model is so good that you still want to use it as a society. And so, okay, so there are issues, and there are more. Just to mention some additional things, there are lots of issues when you're trying to make solutions into the heart of such an important, societally important, and a field of such a long tradition and such well-established thing as medicine. If you try to move into the heart of this process of diagnosis, you need to face a lot of challenges. That's just how it is. Just to have a couple of examples quickly. Quite interesting examples. You have sort of this bottom left area here. There's a lack of theory I wrote that goes not for all machine learning methods, but now I'm sort of mostly thinking of the deep learning methods, those that have a lot of black boxiness to them. It's very difficult to get a very sound theoretical understanding of exactly what's going on in a deep neural network of sufficient complexity, because as a mathematical object, that's a very complicated predictive model that it's very hard to get really a full grasp of, theoretical grasp of, using mathematics, just because it's such a complicated object. So that means there is absolutely a lack of theory in the machine learning part that's related to deep learning. Yeah, then you cannot answer really that question of what makes one model better than another fully, because you don't have the theory to answer those kinds of questions. Turns out that not only are these models extremely complicated objects, but they are often quite unstable, meaning that if you change the input a little bit, you may get a completely different output. And that's used to create like adversarial examples where you can tweak data in some imperceptible way and get a completely different prediction out. So some of these models are very unstable, which is a big issue. And then there's things you have talked about, and there's a lot of things to say about that, but as a software engineering task, machine learning, and maybe even especially deep learning has some unique challenges to it from a software engineering perspective. So you need to establish like some best practices and so on. Okay, but the example from machine learning again, from medical medicine again, there's a lot of interesting research going on important aspects of the medical imaging world, like, for example, accelerating imaging. So there's a technique called MRI imaging that's used a lot, one of the most used imaging techniques beyond simple X-rays and so on. So it's used across the world for many diseases. You do an MRI. Just how that, without going into how the MR machine works in detail, it is the image that you see at the end is not really what's recorded. What's recorded is in the frequency domain. So you're recording some spatial frequencies in some frequency domain, and then you do a transformation into the spatial domain, and that's called image reconstruction, and there you get the images at the end, like the image you see here, like of the brain. But the actual data is not recorded. It doesn't look like this, the raw data. It's in the frequency domain. And there you have to sample that frequency domain. So that's what you do. You're doing some kind of sampling of a continuous signal. Okay, so that takes time to sample very carefully. And then you do the reconstruction, which also takes time. Turns out that you can use deep learning techniques to accelerate this process by not necessarily having to sample that much in the frequency domain. So you can say make it the whole process 10 times faster by undersampling in the frequency domain and still reconstruct images that look like they have high quality. Okay, and even better quality than traditional MRI using some subjective measure from radiologists. Okay, so artificial intelligence creates better, faster MRI scans. That's fantastic. But related to the lack of theory and theoretical challenges in this, turns out that there's a very, very big risk here having to do with the instability of these kind of methods. So in short, as you are well aware, these are machine learning systems, so they're trained on some training data. I mean, you have some input-output, and the input would be then the frequency domain data, and output would be the reconstructed image using sort of the standard method. And then the model is trained to do that process by using examples, right? And then it seemed to work very well, but there is the issue of this is supposed to be able to reconstruct new images, right? That it hasn't seen before. So say a patient with a tumor gets into the scanner and this fast reconstruction is running. There is the possibility, sort of the worst case scenario, but that the tumor is in the image in the frequency domain, but when it's reconstructed, it disappears because aspects from the training data influence the process. Or the other way around, like in the reconstruction, you have a tumor, worst case, but there is actually no tumor. So that's an issue. The wrong stuff is put in the reconstruction. And also then for sure about the reliability of having a small change in the input, like the patient moves a little bit, that could lead to a very different reconstructed image. And that's not good. So these are theoretical issues that these have to face, these kind of methods. And of course, there's a lot of research trying to overcome this, but yeah, it's not easy. And you could then have similar examples in other domains. And also, if you present this to people doing MRI, which I have done, they will also have another objection, which makes a lot of sense. That maybe you're not actually solving the problem that you should solve. It's not the most interesting problem for people actually working with patients and recording MRIs. Because, okay, say you can speed up the recording process 10 times, sounds good. But if you look at the entire process of the patient coming in for an MRI and then the MRI image being reconstructed and sent to the radiologist, the doctor looking at the image for diagnostic reasons, something like 2/3 of the time is spent preparing the patient. So radiographers, they talk to the patient, they place the patient in the scanner, they plan the process, all these kind of things. That's most of the time spent on recording an MRI. So maybe if you really want to make an impact, you should rather speed up that part of the process. And people are working on that as well. So maybe this it's super interesting, of course, this whole reconstruction, fast reconstruction and so on from theoretical point of view and practical point of view, but maybe there are better problems to be solved. So that's another issue with this. Okay, and then there's the workflow integration. You need to, doesn't matter if you have a good model that can do interesting things, if it cannot be used by in the workflow established in, say, the medical domain. And of course, there's a lot of workflow established in any sort of big established domain like medicine. So you need to have it fit into that existing workflow. And that's not where we are at mostly in this field. So this is a figure from Erik Topol pointing out sort of the steps before you're actually making something that has some impact in healthcare. First, you make your model, your machine learning model, and then you validate it, meaning you test it, right? In silico, meaning on the computer. So you're sitting on your laptop or your workstation or your cloud solution and developing a method, and it performs well, it seems, on the data you have, and then you publish a scientific publication. That's the common thing, and maybe you publish the code and everything, so very good. And then you stop, because mostly there are no incentives to move to the right, really. So most research is happening only there. But of course, for this to have some impact, you first have to validate it in the real world, a so-called clinical validation, where you have a big study of lots of new data coming in and see if it actually performs as expected on new data and the more real world data. So that's the step where if you can do this, then you can get like FDA and CE approval and actually have a product that can be sold. And then you, of course, can publish here, but these publications are very different. It's not about the technical details, it's about the clinical validation. So there are much fewer here. And then even if you have an FDA approval, approved product, approved to be used, it's not like it can directly be implemented in healthcare, because the approval process of these products is not very extensive. So it's not like the hospital. You can go to the director for radiology and say, let's just buy this product. It's approved. They will have to do a big process of checking whether it can work in our hospital. So there's much fewer things going on here in the world. So we are mostly on the left side, but there are things pushing, fortunately, the machine learning research into clinical validation. Many things are pushing that direction, but it's a hard thing to push that direction because the incentives for researchers are mostly to publish, sticking to the left side. Okay, but that leads us to sort of the ambition of the center where I'm working at Haukeland, and also Satish is working, so it's likely to mention this. The Moon Medical Imaging and Visualization Center, which is embedded in the Department of Radiology at Haukeland and supported by the University of Bergen, Høgskolen, Helsebergen, Trondheim Stiftelse, and yeah. So here we are working to try to move to the right side, in a sense, towards implementation of machine learning closer to actual patient care. Yeah, so we are sitting here at Haraldsplass and really trying to make things happen. And one may say that we have like 3 pillars of what we're trying to at the center when it relates to machine learning. It's about research. It's a research center. So we are still mostly on the left side in that figure, on the research side. Also education, we put a lot of emphasis on education because you need that to make these things work. You need to make like a good ecosystem of people and expertise to make things happen. And then importantly also translate this into actual practice and innovation. So on the research side, we have multiple projects going on. I will not go through them, trying to make interesting solutions across many different domains, and then see if we can move those towards clinical practice by at least testing them out closer to clinical practice and working closer to the expertise than what is often done. By the way, we also have a bunch of master students from the software engineering master's degree that have gone through our center, and people are here working on very many interesting things, from robotics to electronic health records and many other things in between. Okay, but let me just show you one very important thing that we're trying to do here, the so-called WIML project, which stands for Workflow Integrated Machine Learning. And with what I've told you, it's obvious that you need to do something like this. And that's what this project is trying to do. You need to create a sort of a home for AI solutions inside the hospital. Otherwise, you will always just work on the left side, you know, in that figure, on data that you downloaded and just playing around with. You cannot easily move towards clinical practice without actually being able to test things out inside the hospital. So this project has at least two goals. It's to facilitate the testing out existing commercial potential solutions in some environment where we can control everything. And also we want to use this for all our research, really. That's the ambition, so that we're not just playing around with some data that we downloaded, but we're actually testing out the solution in a system that mirrors like the hospital system. Okay, and also briefly on the education side, one thing that we find very fruitful is related to the point I made, that you need the domain experts on board to do high impact things, is the course we have on as part of the elective courses on at the medical faculty at the university, where the medical students are being educated. So it's a course where people from software engineering and other technological domains can work together with medical students on these topics of machine learning in the future of medicine. And that's in line with what the government wants to do, like really put this education of machine learning into various domains where it seems to be potentially have a large impact, and actually teach the domain experts machine learning. And we also then do it in a way that the machine learning more machine learning students, software engineers, are also part of this. Yeah, so that's something that will likely come in many domains, not just medicine, because there is a need for interdisciplinarity identified by the government, at least. Okay. So let me, I'm spending a lot of time, sorry about that, but let me just finish up by broadening the perspective a little bit. So we talked about medicine, but this landscape where you can apply the similar kinds of things that I've been saying related to medicine is much larger. It goes into many other fields as well, right? So medicine is an example, but you could tell similar stories in other fields, many other fields across like the natural sciences and technology, and into more even journalism and society at large, and agriculture is a big deal for machine learning, and so on and so forth. So you could tell the same story in many other domains. And if you want to apply machine learning into any of these domains and more, you are led to the machine learning engineering perspective. So you've seen this figure, right? You know that the model is a very small part of a larger system that you need to set up to make actual solutions. And you can say that machine learning engineering, actually practical machine learning, that's a combination of computer science, software engineering, definitely, and data science for machine learning. You need all of this. And you also, from this other figure we had, you see that there's a lot more than just like the model, the bottom part here. That's just a small part of it. And And you should actually be very happy about this picture if you're interested in moving into this field, because if you just think back to what you've learned in your bachelor's degree, the courses you have taken, or some are elective, so you may have taken in the catalog that you did for the software, the data engineer bachelor degree, you can make the point for each of them. You can say that you can link it to this picture. So databases, for example, that you have learned about, of course you need to know about databases, because that's where the data is, if you really want to make a machine learning solution. And web applications or distributed applications or application development, of course, because you need to know about how this can be deployed and be made available as some kind of application, and so on and so forth. You can make the point for any course you've taken that actually that course is very relevant knowledge for this machine learning engineering perspective. So you are actually doing the bachelor degree that one should do if you want to really do practical applications of machine learning. And also, just last slide, but you also know that should you want to continue the master's degree, then the kind of, and you want to do this kind of work, machine learning engineering, then I think continuing in some software engineering direction is a very sorry, good way to go. So that could be our master program at the Högskolan, but it doesn't have to be that, of course. But keep that in mind if you really want to go in this direction, that you should keep up the software engineering perspective as well, and as not just the machine learning perspective. Say, depends on what you want to do, but if you want to create these solutions. And if you continue on our master's degree, we have a course that sort of follows the 158. So 158 is sort of machine learning engineering, and then 255 is deep learning engineering. So that's specifically these kind of methods, but it tries to keep the same perspective as 158 on the engineering point of view. So that's just so you know that exists. And if you are interested in the medical applications more of machine learning, you may consider coming to our conference at the center beginning of December, where machine learning plays a large role in the program there. So you can check it out on the website. And also the course LMed 219, should it be fit with your schedule to join such a course, it runs in January, this January, from January 4th till 27th or something, 6-credit course, so relatively intensive, 1 month. But if it fits with your plans, you may consider joining this, and then you will get to work side by side with medical students on these topics. And if you're interested, just let me know. Okay, so a little bit of advertisement at the end there. But that's it. And hopefully you are able mentally to translate everything I said about medicine into other domains you're interested in, like agriculture or finance. Same things apply. Thank you.